So let's start with option Greeks. So option Greeks are nothing more than derivatives of the Black-Scholes pricing function with respect to the underlying pricing parameters. In particular, we consider, actually the industry consider four main first-order Greeks plus another second-order derivative, which is the gamma. So consider a plain vanilla option, which depends on a strike price, on an expiration date, and is evaluated at a given time t. So the delta of the option is the first derivative of the Black-Scholes pricing function with respect to the underlying level. Instead, the theta of the plain vanilla option is the derivative of the Black-Scholes pricing function with respect to the elapsed time, and this typically measures the depreciation, so the time decay or the depreciation in value of the option as the time elapsed. Then there is the vega, which is the derivative of the pricing function with respect to the sigma parameter, so the underlying volatility. And finally, there is the rho. The rho is the derivative with respect to the short rate level. So we will consider first a numeric implementation of these first-order derivatives. And finally, we will compare the numeric implementation with the analytic expression that is available for the Greeks under the Black-Scholes model. So, let's consider a general method to compute numeric derivatives. This is called finite-difference methods. I suggest you to go either to Wikipedia or to take a look at this post here, which explains step by step how a finite difference method is. So the idea is very simple. Instead of considering the exact expression for the derivative of a function, we want to consider an approximation of the derivative of a function in a certain point, for example at x0. In the example that we consider as a function the function sen of x, so the sinusoidal function, and as point x0 equals 0. So it can be shown that the central finite difference approximation of the first derivative of the sen of x, which should be cos of x, so the cosine of x, is given by this expression. So you evaluate the function at two near point, one slightly above and the other slightly below your central point, divided by the distance between these 2 points, to 2 epsilon. Epsilon is a small number, and it's granted that under certain regularity condition of the functions, the approximation error that you make, so the rest of the expression that would make this expression exact, is at most big as epsilon to the power 2. So it's very small, because you know a small number exponentiated to the power 2 is even smaller. So let's consider the finite difference approximation of so here is a very simple example of implementation of this formula. And let's consider as a function the sen of x, and as the exact derivative we know is the cosine. So this plot, which is defined in plot compare, which is in the utility, we go back to this later when we introduce Black-Scholes analytics package. So this plot compares on the left you have the numerical approximation of the derivatives. On the right you have the exact approximation, so the reference function, so that is our benchmark. Then here is the difference, so the absolute difference between our numerical approximation and the cosine, so and the exact evaluation. Here is the relative differences, and on the bottom you have the same but in absolute terms, so taking the modulus of the terms. So we see that actually the biggest differences, at least in relative terms, are where basically the sin is basically it's so when the derivatives is 0 actually. Okay. Okay. So this is a very generic example of finite difference methods. I have implemented in the NumericGreeks class the implementation of finite difference methods for option Greeks. So considering finite difference methods, we can have a look at this now. So let's take a look. So it's pieback shows is in utils numeric routines. Here is our NumericGreeks class. This is a very simple class which implements methods which takes in input a financial object that basically has a price method, and basically it considers the delta, so the derivatives with respect to the parameter s, the gamma, so the second order derivative with respect to s, we'll come back on this later, the vega, the theta, and the rho. Each of these is implemented according to the formula that you have seen before. Okay, so we instantiate the market environment, we instantiate our plain vanilla option, so a vanilla call, and from these numeric routine modules we import the NumericGreeks class. So we instantiate the NumericGreeks class with our vanilla call, and then we can compute the numeric expression of all these of this vanilla call for all the Greeks. So here is the delta of a vanilla call for a given level of a given range of the underlying level. As you can see, it goes typically from 0 to 1, basically for from deep out of the money vanilla calls to deep in the money call. Okay. Then there is the theta. Theta is typically the derivative of the pricing function with respect to the time. Theta is typically negative, and this is because as you can see, so it's always below 0. This is because basically options tend to depreciate, so to lose value as time elapses. So the derivative with respect to the time is actually something which is negative. Then there is the gamma. The gamma is the second order derivative with respect to s. So the second order derivatives according to the finite difference method is given by this expression here. So and the truncation error is still of order epsilon to the power 2. So basically you take the pricing function evaluated at your level minus epsilon minus 2 times the pricing function evaluated at the central point plus the pricing function evaluated at the S0 point plus epsilon divided by epsilon squared. And this is the gamma. So the gamma is of course measure basically the convexity of the pricing function, and it is bigger for options around at the money. As you can see, our option is an option that has strike 100, so the peak is around 100. So basically the convexity of the option is typically actually this is just a qualitative consideration, but typically is not exactly at the strike at the money level, but around that level. It's where the gamma gets its peak. So you might wonder what is the role of the epsilon. So the epsilon is basically the distance between these consecutive points that we consider to take differences. So you might be wondering whether if we decrease the level of the epsilon, we get more precise numeric derivatives. But this is not always the case, because since we are implementing this on a computer, there are of course truncation error given to finite precision of the machine that lead to very unstable results if you take an epsilon too small. For example, for epsilon equal to the 1 to the power minus 5, you get this instability, which increase if you consider 5 to the power minus 6, which basically mess everything if you even consider epsilon given 1 over 1 million. So it's even if analytically it's true that for epsilon, in the limit that epsilon tends to 0, you get a perfect, so an exact result. Of course, this is not applicable one by one in a computer. Okay, so this is typical. So a good compromise between having a stable result and having a meaningful result is, in this case, having 1 over 10,000. Okay, epsilon 1 over 10,000. Then there is the Vega. The Vega of the plain vanilla call measure the sensitivity with respect to the underlying volatility, and still this is also a Greeks that increase and its maximum around at the money level. And finally there is the rho, so the effect of the short rate. The effect of the short rate is a bit less common, or at least less known, but it's the effect of basically it's the effect of the discounting with respect of future payments. So this is the effect of the short rate. Of course, we could have used also put options. So and this is the typical delta that comes. So it's still increasing, but it goes from -1 to 0. Okay.